It's Monday morning, you open Spotify, and Discover Weekly is just ready. Every single song just fits in, and it gets your mood, your taste, and every single vibe. But how does it do this?
Here's what's actually happening. Every song on Spotify is described by dozens of audio features: tempo, energy, loudness, how danceable it is. Each feature is a dimension. So every song is literally a point floating in a very high dimensional space.
And somewhere inside this cloud is structure. But finding this structure is really difficult. Your standard tools will look at this cloud and just flatten it. They miss the shape completely.
So how do we actually solve this? We treat it as a graph problem. We connect the songs to the nearest neighbors, build a network, and use the mathematical properties of that network to unfold the true structure of the data. That's what this project is about, and that's what graph theory solves for you.
Discovering nonlinear structure, a graph theoretic approach to dimensionality reduction.
PCA looks at your entire dataset and finds the directions where the data spreads out the most, the directions of maximum variance. It then rotates your axes to line up with these directions and drops the least important ones.
This is what that data actually looks like. Millions of songs, dozens of features each. It's way too high dimensional to visualize or work with directly. So we need to compress it. Find a smaller space that still captures what matters. That process is called dimensionality reduction. The classic method for this is something called PCA, Principal Component Analysis. And for a lot of data sets, it works beautifully.
For simple linear data, this is elegant. 2 components, 99% of the variance captured, done.
But the real music data is non-linear. The genres don't sit in neat straight lines. They curve, they twist, and they overlap in complicated ways. A fast jazz track and a fast rap track are of the same tempo, but they are musically worlds apart. PCA only sees straight line distance, the Euclidean distance. It has no idea how the two songs are really far apart in the real shape of the data. So actually, when it tries to flatten everything down to 2 deep, it just crushes the structure. So any two songs that are different in genres may end up on top of each other, and any recommendation based on this would be a complete mess.
Here's where our approach comes in. Instead of analyzing the whole dataset globally, we ask each song a simple question. Who are your nearest neighbors? The songs closest to you in feature space.
The graph becomes a skeleton of the manifold. It has learned the shape of the data. We then assign weights to those edges using the Gaussian kernel. Songs that are very similar get strong connections. Songs at the edge of the neighborhood get weaker ones.
From this graph, we build 3 matrices. The weight matrix captures how similar each pair of connected songs is. The degree matrix captures the total connection strength of each song. And the graph Laplacian is simply L equals D minus W.
The Laplacian has some remarkable mathematical properties. It's always symmetric. It's always positive semi-definite, meaning all of its eigenvalues are real and non-negative. And it always has at least one eigenvalue equal to 0. That 0 eigenvalue isn't a flaw, it's information. The number of 0 eigenvalues tells you exactly how many connected components your graph has. One connected genre landscape, 1 0.
Here's our full approach. Step 1, we build the k nearest neighbor graphs, and then the step 2, we weight the edges, we compute the graph Laplacian, and then we solve the eigenvalue problem, and then the eigenvectors are our new coordinates in the new space. So here's the result. On the right, we have the PCA. It collapses the rule, the colors are mixed, and the structure is all lost. And here, on the left, we have the Laplacian eigenmaps. It unrolls it perfectly, and the colors flow smoothly, and the true two-dimensional structure of the data is just preserved. So graph theory gave us a way to see the shape hiding inside complex data, and by thinking locally, neighbor by neighbor, and using the spectral properties of the Laplacian, we can unfold manifolds in linear methods that linear methods cannot even recognize.